Okay, this is additional video for chapter 8. We will have a chapter 8 in our semester. This is the Arclang and the surface area. Okay, so I decide to give you this chapter 8. Okay, let me start with the random graph like that, and we call this y equal f of x. Okay, the arc length means we need to measure the length of curve. Okay, for example, if we have this y equal f of x, okay, if you want to calculate the length, what we can do, okay, now if we decide to take on this curve, divide into some points, let's say we got it from P0, P1, let's say P2, okay, and P3, and then another one, then another one, and then until the very end, let's say until the end, the Pn, and this one is we call Pi, and let's say we call this Pi minus 1, okay, and we call the first point we observe we called A, the end point we called B, okay, P1 we call x1, P2 we are going to name this as x2, and the other one here we're going to call this xi minus 1. This will be xi. Okay, now one way, or maybe this is another one here, any let's say x3, we can call it x3. Okay, now to measure this length, one method or one approach is to take a lines, okay, connecting all this point with a straight line. So first is that, second is that, this is the third, this is the fourth, okay, and this will be the fifth, and this will be the last one. Okay, now we have all these straight lines connecting all the points in between the curves, right? So if we take each distance, okay, we take each distance. So imagine we are taking the distance, this distance. Taking distance between P, all P, okay, then we can write something like the length of curve. We can imagine this distance we are going to plus with all the red line, because so the straight lines we are going to add, and we are going to have, okay, if the n is getting larger, okay, we are going to have Sn going to infinite number, then the sum The length is the sum of the difference or the distance between pi minus 1 and pi. Okay, so this means the distance. Okay, distance between the point P, right? And if we let the delta y is the difference between yi and yi minus 1, okay, so we have this, let's say we have the difference, okay, or maybe here, or maybe here is much more easier to see. This is the delta y. Okay. Then the distance, okay, the distance will be this is xi minus xi minus 1 and plus that squared and we can write this as the delta x squared plus delta y squared. Okay. And in mean value theorem, we know that the difference on the functions okay, or you can also imagine this as in your line equations, y, right? So we can say that the delta y is equal okay, so we can exchange this, okay, so if we want to write in terms of, let me write here, we can write this as the delta y becomes f prime, okay, we can factorize the delta x squared, so this will be 1 plus or we can write this in terms of just 1 plus f prime and then delta x. And our limit here becomes the integration. So let me write the limit. Limit and we say that in our definition of the limit and the sum, we get the integral from a to b, and we got this f prime x squared dx. Okay, and this is the theory, the first theory. of the arc length. So L is the arc length. Okay. However, for me, to get a better idea on the arc length, we can have another approach, and I think this approach is good, but I prefer the other one. Okay, let me show you how. Let's say that's our f of x. Okay. Now the idea is we are going to have some tangent line like that. Okay, and we call this tangent as a dl. Okay, and this tangent is based or composed on two elements, which is dy and the x. So let this dl is really small. Okay, and we can just using the Pythagorean theorem of the triangle, and we know that this will be dx. Okay, now we are going to have let's multiply this with the x squared and divide by the x squared. Okay, so we are going to have dx is going to be outside. Okay, dx is going to be outside. We are factorizing the x, and the rest will be like that. And we have dl is okay, that's the dl, and we can integrate these two elements, left and right equations, and we got that the L is integration from, let's say, a to b of our 1 plus okay. This definitions for me is much more easier to illustrate, and you can just using this triangle, the Pythagorean theorem, to prove that we can have the arc length, the L, as 1 plus dy dx squared dx. However, we also have other forms. Okay, so for example, I can take this in another approach, and we take it to dx over dy like that. So we will have 1 plus dx over dy squared and then dy, and we have L, let's say this is c to d of 1 plus dx over dy squared, and then this is dy. We can also have that in our terms. Okay, we can exchange x with y, so we can have functions of y, right? Okay, so that's the arc length. In arc length, we also know that we can have functions, arc length functions. Okay, so let me write first. This is arc length functions. It's similar to the fundamental theorem of calculus, similar looking. So let me write that if curve C has equation y equal f of x, okay, and a is and x is from a to b, the interval, and let s of x be a distance, okay, along the curve C, okay, from, let's say, B0 to some Q. Let's say Q is X, f of X, okay. So this is what we are having. Okay, let's say this is a curve C, okay? And this is A, let's say this is X, okay? So we call this segment of C is S of X, okay? So just a one segment, okay? So we are going to define our arc length in the functions. So S is a functions, okay? And we are going to have integration from A to X, okay, of the 1 plus f prime t. Let's say we are going to have the variable t, dt. And this is actually similar looking equations with the fundamental theorem of calculus, okay. So by fundamental theorem of calculus, okay, we can also rewrite this as we can derive this and became precisely this equation, okay. So we can also write the arc length in a functions, okay. We call this the Arclang function. Okay, that's the first section of chapter 8, the arc length. Okay, let me give you another one, the second section, which is the area of surface. Okay, let's say we have a curve C like that. And let's rotate this curve C. Okay, let's rotate. And it will create the, let's say if we take this area here, we take this, it will create a certain of solids. And the question is, I want to know the surface area of this, okay. Let's say we have, this is some L, okay, some length there, and we have the radius, right? We have the radius, let's write R, okay. Now if we look at the cylinder, with the radius R and height is H, okay. If you want to know the surface area, the rectangle part, okay, so if we take this and we can take it into a rectangle form, this length will be 2 pi r, the circumference. This will be the H, and we called it the lateral surface area is 2 pi r H, right? Okay. Now if we take a cone, okay, with the radius R and the length L on the sides, okay. If we cut, okay, let's imagine we are cutting this let's cut this. Okay, cut open. We are going to have let me move this a little bit left. We are going to have, say this is okay. Okay, let's say that our cone. Okay, this will be the L, right? Yeah, the same L. And the rest of it, this part, this will be the circumference, right? From the circumference, the same circumference here. So this will be 2 pi r, okay? Okay. Now, if you want to know the area, right? The area, we call this as the sector. Okay. The sector has the area. If we have angle theta there, we will have theta over 2 pi multiply with pi L squared, or we are going to have half of L squared theta. Okay, and we know that from the 2 pi r, that the 2 pi r is equal with the L multiplied with theta. Okay, so that we can have L is 2 pi r divided by theta, or we can say L theta is 2 pi r, so we can have half 2 pi r L. So this will be pi r L, the area. Okay, now we are going to use this area, or use this method, okay, to look on what we have here, because certainly we have a circular shape, and we have some L here, right? And if we imagine this, letting these shapes become a cone, let's draw the cone. Okay, so let's imagine we cut the cone and we are going to evaluate this part. So let's imagine we cut the cone. Okay. Okay, so let's name some variables. We have radius. Let's say the radius 2, and this will be radius 1. Okay, and we have the L1 and L2. So the idea is we are going to calculate the whole cone, the full cone, and we are going to minus the small cone on the top. So we will get the bottom shape, right? So let me write the area of full cone is pi r2 and L1 plus L2, or let me write this just L. Okay. And area of small cone will be pi r1 and L1, right? And we take this, subtract, okay? We call this a frustum. Okay, this is called, we call a frustum. So pi r2 L1 plus L minus pi r1 L1. Pi r2 L1 plus pi r2 L minus pi r1 L1. Pi L1 R2 minus R1 plus pi R2 L, and we can have pi R2 minus R1 L1 plus R2 L. Okay, I think we can stop here. Now, by looking at the triangle property, okay, we are having, let me write here, okay, and if this is R1, this is R2, this is L1 L, okay, we can write down L1 over R1 is equal L1 plus L over R2. We can write this as L1 R2 equal L1 plus L R1. Okay, and if we write down the expansions and we set up some grouping the L1, okay, grouping the L1. Okay, we can have this, okay, we can have these relations, and then we can use that to change the hook up into here. Okay, so this will be R1L. Okay, now if we have let R be average radius, which is half R1 plus R2. Okay, now 2R is equal R1 plus R2. Now this will be pi R1L plus R2L, okay, or pi is R1 plus R2L. And if this is going to be 2R, so our area will be 2 pi RL, and this will be the surface area of the frustum. Okay, okay, now we are going to use this approach to take on into our curves. Okay, this curves here. Okay, let me write in the next page. Let's say this is a PO, a PN from A to B like usual. And let's say we have in the middle is a PI minus 1, PI, and we draw the curve that is having rotations here. Okay, we are having rotations, and we have L about that part. It's similar with the arclang we have done before, and let L is the distance between PI minus 1 and PI, and the average radius of the function will be half. Okay, let's take that as the average radius, which is going to be around here. Okay, the average radius. Now surface area, based on the Frustum approach, will be 2 pi. Okay, this is the radius divided by 2, and L will be from the distance of pi minus 1 and pi, right? Okay, now based on we have from the previous arc length, we can input the arc length equations. We can cancel this, and we can have this is using the using that part. Okay, okay, now this part here, okay, this y, okay, this y here, can rewrite this in terms I don't think we need to cancel this. We need to rewrite this in terms of this part. We can write as the radius, right? Which is we can have average functions as the f xi, okay. And we can approach this using the limit concept. Okay. And our S or SA surface area All right, now as a summary, if we have this function here, and we will have rotations about x-axis, okay? Then the surface area, if you want to find the surface area of revolutions, usually we are going to use that word, revolutions. So rotation is x-axis. Okay. The surface area becomes 2 pi y and then the s. Okay. This is the radius. This is the arc length. This is y equal f of x. So this will be an f of x, and your ds will be 1 plus dy dx squared dx. Okay. So automatically, this ds will be calculated into a dx. Okay, automatically when we are looking here. This is the y, right? Y is f of x. It's similar with what we have done here, that we have f of x and we have a dx here. This is what this illustrates. Okay. And if we have another case, let's say the same function, maybe around here. Okay. yeah, same function. Let's say the same function y equal f of x, and we are going to rotate the curve about y-axis. Okay, rotations x-axis. So this is rotations y-axis. Let me take a little bit down. Okay. So we will have, let's say this is the radius, or let me draw the how it looks like. Although it's not really a center and proportional, but you can see that we have the radius now changing from y to x, right? This is x, right? Okay, so we will have the surface area is 2 pi x, and again it's the x, but in our case here we are going to let this x is in terms of function of y. Okay, so this will be the radius, this will be the arc length, and our arc length here we need to also mention in terms of dy. So we are going to have 1 plus dx over dy squared and then dy. So you need to exchange y with x or x with y between these two. Okay, I hope you get a little bit concept of the surface, okay, surface area of revolutions, and also the arc length. Hopefully we can have more exercise about this, and yeah, I can give you with another video for the exercise, but let me just stop here for the theory about the arc length and the surface area of revolutions. Okay.